Welcome to your next video where we will be discussing distance and midpoint in the coordinate plane. Now, the coordinate plane is our Cartesian coordinate plane with our x and our y axis where we could plot points or graph lines. And so just as a little review, we need to talk about and see if you guys remember how to plot points in the coordinate plane. So the first value, 14, and then the second value, -2, you got to remember which one's the x and which one's the y, and it simply just goes in alphabetical order. Your first value is your x. Which one is the x-axis? Well, if it's not labeled, it's always the horizontal one. And our second value, -2, is our y-coordinate, and the y-axis, if it's not labeled already, like you can clearly see here, the x is kind of blocked over here by the pirate, the y-axis is the vertical axis. And so that tells us we need to go up or down. Now, if we move to the right on the x-axis, we're in positive territory. If we move to the left on the x-axis, we're in negative territory. Up on the y, positive. Down on the y, negative. So 14, -2, we'd move 14 to the right, and we would move down 2. And there's our pirate, right in the eye. So if I asked you, what do you believe is the distance between these 2 points? And some of you might be questioning me and going, well, isn't that kind of an obvious answer? I mean, can't I simply, we could make a segment, right? And want to know, well, how long is that segment? That would really be the same as the distance between those 2 points. And well, let's see. And we're going to use something what I call the bunny hop method, if you will. It's 1, 2, 3, 4, 5. It's 6 units long. So the distance between those 2 points is the same as the length of the segment in this case, which are both 6. And we could simply just count that. And yeah, that is a perfectly plausible way of doing that. Is there a more involved mathematical way of figuring out the distance between these 2 points? Yes, and we'll get there. Just not with these 2 points. So these 2 points, could you easily find the distance? Could we do the same idea that we just did before? And we can, right? So we can connect these if we needed to. So we're really talking about the distance between these 2 points is the length of this segment. And again, could we just bunny hop and go 1, 2, 3, 4, 5, 6, 7, 8, 9. The distance between those 2 points is 9, or the length of that segment has a length of 9. And yeah, we can still do that, right? But what if I had the points go this way? I mean, I can still make a segment, right? I can still make a segment here, but can I still just simply count the number of units down the road here, down this segment? Can someone really go like 1, 2, 3, 4, 5, 6, 7, 8, 9? That wasn't quite a full hop there, like 9.5, 9.4, and then we get kind of stuck there, right? So we cannot just simply count the distance like we could in the 2 previous examples. And so why is that? Why can't we count going more in a diagonal type of direction here? And it all boils down to our coordinate plane. Our coordinate planes are made up of little squares. And those little squares have side lengths of 1, right? So this is a 1, this is a 1, this is 1, 1, 1, 1. So the squares are in a kind of vertical, like the y-axis, and horizontal, like the x-axis, orientation. So that's why we could count vertically or horizontally between 2 points. But in this case, this isn't vertical or horizontal, so we have to come up with a different way. Now, some of you may already have some idea of what we're going to do next, and that's awesome. But we're going to have to kind of, I'm not going to say manipulate, we're going to have to look at these 2 points in a little bit different way. And we're going to use something that I'm pretty certain that you guys have done and worked with previously. Maybe it was in 7th grade or 8th grade. I'm not for sure. But I know you've definitely seen this particular topic. So I'm going to switch over real quick. Nope, not to that. To this website. And these aren't the exact 2 points that I had on the in my lesson there, but this gives you a rough idea of really what we're going to look at. We're going to take our 2 points, and instead of just directly counting from those 2 points, we're going to have to make a right triangle out of this. And we're going to think about this as a kind of a vertical piece and a horizontal piece. And those vertical and horizontal pieces we can count, right? So I can drop down 3 units, and then I can shoot over to the right 5 units. So I know those 2 pieces, right? And if I know 2 pieces of a right triangle, is there like a famous geometrical theorem that you guys know of that would help us find the third side of a right triangle? You guys remember anything? Maybe involving the beginning of the alphabet, like with A, B's, and C's, and there's something weird about that, right? So we need the Pythagorean theorem. So on your notes, I didn't really put any of this down in your notes because I didn't want to reveal what we were going to do. So I tried to leave you a lot of space in your notes there to write this down. So go ahead, and I know this may take a little while to fully all write down here, but just try to squeeze this in, and then we'll talk about how to apply the Pythagorean theorem to our example. Now, you can also pause the video so you can start writing this down. And this isn't common that I will just kind of spring forth a lot of information on you at once. Usually it's already in your notes. So this is a very rare occurrence where you'll be like, oh my gosh, this isn't anywhere in my notes and I have to write this down. So if you need to pause the video and do that. So the Pythagorean theorem. If a triangle is a right triangle, this has to be a right triangle. And I know we really haven't got into classifications and what right angles look like, but I'm pretty certain that from previous experience, you know that a right triangle must have a right angle in it, and a right angle is a 90-degree angle. Okay? So we need to see a right angle, which is usually a little box down in the corner. Now, then, if we have a right triangle, then a squared plus b squared equals c squared. All right, now the A and the B represent what we call the legs of the right triangle, which are adjacent, and adjacent just means right next to. They are adjacent to the right angle. So adjacent means right next to it. So here's my right angle. What's right next to the right angle? Well, side A and side B are right next to it. And those, again, are the legs of the right triangle. Now, does it really matter where the A and the B go in this triangle? Could B be this vertical piece and A be the horizontal piece? Absolutely. But the C must be this particular side. So let's see here. C represents the hypotenuse of the right triangle, which is always opposite of the right angle. So if I talked about the side of the right triangle that did not touch in any way the right angle, I mean, I was just kind of shoot directly across from the right angle. There is my hypotenuse. So this side must always be the hypotenuse. The C side is the hypotenuse. The A and the B are the legs. It doesn't matter which leg is A and which leg is B. But C must be the hypotenuse. Okay, so there's our quick, hopefully, review of the Pythagorean theorem. So now let's put the Pythagorean theorem into play. All right, so again, here's our 2 points that we were looking at earlier, and we want to make a right triangle out of this. So usually what I'll first start with is I'll connect together my 2 points, because that's the distance, that's the length of this segment that I really want to find here. So I usually start with this piece here, and then you can drop down. No, that's a little off. We'll make it a little better here. We can drop down and over. And it's not perfect looking in here, but there is a natural 90-degree angle, right? Okay, so now I'll start off with the Pythagorean theorem. And we need to identify the A, the B, and the C. Now, the distance between our 2 points, that will always be our C side. That will be the hypotenuse. So we can always label that piece C. Now the A and the B, it doesn't matter which one's A and which one's B. Usually I like to call the smaller leg A and the longer leg B, but that's just personal preference. Now again, to figure out the 2 legs, we just get to count. we get to go, there's 1, 2, 3, 4, 5. So this vertical piece has a length of 5. And then over here, we have 1, 2, 3, 4, 5, 6, 7, 8 units of length for our horizontal piece. So me, personal preference, I will call the 5 the A and the 8 the B. Just smaller, bigger, that's just the way I roll. So we've got 5 squared plus 8 squared equals C squared. And so now using our order of operations, we have no parentheses, but hey, we have some exponents here. So I know I've had students in the past go, oh, look, 5 plus 8, that's 13, and then 13 squared is 169, but the order of operations doesn't work that way. So exponents first. 5 squared, 25. 8 squared, 64. And then we can do the adding here and get 89 for C squared. But that's not the length, 89. We got to do one more algebraic step here because we need to get rid of the square on the C. And so we need to do its inverse operation, just like subtracting is the inverse operation of adding and multiplying is the inverse operation of dividing. What is the inverse operation of squaring? And that would be square rooting. So algebraically, we need to square root both sides. And then the square and the square root cancel each other out. That's why they're inverse operations of each other. And then the square root of 89. Now, typically I would say we're going to work on simplifying square roots here. But the way that the book kind of tackles this initial round of square roots is they just want you to approximate what the square root of 89 is. And this is where you're just going to grab your calculator. And so if I go 89 square root to square root 89, we're going to round these. It really doesn't matter. And this is where I'm going to use a wavy equal sign. This means approximately. This means I'm going to be writing a rounded number because the square root of 89 is irrational. It goes on and on and on and on forever. There is no end. And you might go, no, there's an end. It ends at 1. But it doesn't really end at 1. That's just all what the calculator shows me. And maybe your calculator shows you more digits past the 1. Me, personal preference, I like to round things to 2 decimal places. But sometimes the book may say round to the nearest tenth, to the first decimal place. So I'm going to stick with my personal preference because I always like to do two decimal points here. So this would be 9.43. The digit after the 3 is a 3. So since it's below 5, then I do not round that first 3 up. So this is approximately 9.43 units long. Now, I'm going to throw this out here just because this specific example happens here. If I said round to the second decimal place and you're looking at that 3, I have had students in the past go, well, if you look at that 3 that's after it, oh, but then look at after it, there's a 9. That 9 would bump that 3 up to a 4, but it still doesn't affect it. So whatever decimal place you're rounding to, you only look at the next number. You ignore all the other numbers that happen after it. All right, now we get to what's our official first example here. So write the coordinates of points A and B and then calculate the distance between them. All right, so let's see. A is at where? -1, -2, -3, -4, -5, comma 1, 2, 3, 4. So -5, comma 4. And B is located at 1, 2, -1, -2, -3, -4. So 2, -4. Now, if I'm using my graph here, if I'm going to set up the Pythagorean theorem, there's the distance that I really want to know. And then I could just drop down and over and make that right triangle. Now, I also want to throw this out here. Could I have went right and then down and made that right triangle? And the quick answer is yes. Those are the same triangle. They are just in a different transformation. One has been reflected or rotated versus the other. So it doesn't matter if you draw your right triangle this way or the other way that I had. I usually like my right triangles with the pointed end up, but it doesn't matter if it's pointed end up or pointed end down. It'll be the same leg values for A and B. All right. Now, I'm going to show you a slightly different way here. We're still going to use the Pythagorean theorem, but I'm also going to show you a secondary way of really setting this up. So when we have this set up here, you'll notice that I set my coordinates up, like I stacked them on top of each other, right? So I'm going to do the regular Pythagorean theorem first, and then I'm going to come over here and show you a different way that doesn't require the graph, okay? But we'll still get the same kind of setup, all right? So here's the way that we just did it in the last kind of discovery example. We counted our legs here, 1, 2, 3, 4, 5, 6, 7, 8. So this has a length of 8 vertically, and then 1, 2, 3, 4, 5, 6, 7 horizontally. And there's our A and our B values for our Pythagorean theorem, right? And here's our C side. And so Pythagorean theorem, we would set this up, and I'm not going to finish this, but we'd go, let's say 7 squared plus 8 squared, or 8 squared plus 7 squared, it doesn't matter, equals C squared. And we would finish the rest of that problem. But I'm going to show you how we could also get that 7 and that 8 without the use of a graph. And this is where you're going to save yourself a little bit of time. But I'll show you how all of this kind of comes together in the next slide. Okay? So if I want to find the distance between 2 points, I'm really saying I want to find the difference between the 2 points. And so mathematically, if I want to find the difference between two things, then would I add, subtract, multiply, or divide my two things? And if I want to find the distance or the difference between, I would subtract. And so that's what we're going to do with our coordinates. And that's why I stacked them up vertically like this. We're going to do not just one round of subtracting, but 2 rounds of subtracting. Why 2? Because we have 2 coordinates. We have an x coordinate and a y coordinate. So when I set these up, I'm going to look at my x coordinate, whatever happens to be the first x coordinate, and we're going to subtract away the second x coordinate. All right, so we have negative 5 minus 2. Negative 5 minus a positive 2 would be negative 7. Okay? But then we got to do a little bit more subtracting because we have y coordinates to subtract as well. So 4 minus negative 4. Well, what happens when we subtract a negative value? Well, we end up adding it, right? So this is really saying 4 plus 4, which is 8. Now, that negative 7 and 8, do those numbers look fairly familiar? Like, oh, I don't know, it's maybe the same as this 7 and the 8 for the Pythagorean theorem? And some of you might go, well, wait, it's close, but that 7 was negative, and the 7 we got here was positive. And that's true. But here's the thing. Coordinates can be negative, right? We can move in the left direction in a negative direction, or we can move down in a negative direction in the y axis here. But anytime we're talking about lengths of a triangle, we can't have negative lengths. So the one way to alleviate the difference between we can have negative values in coordinates, but we cannot have negative values in actual length is we're going to do something, and I just kind of gloss over this, if you will. But this negative 7 is really a positive 7 in length. It's really a negative 7 in terms of coordinate math, but we want to convert it to a length. So what we're going to do is take the absolute value of that negative 7 and turn it into a positive number, so now it's representative of length. Okay? So instead of actually taking the absolute value, I'm telling you now, you will take the absolute value, which just means we're going to make that negative into a positive. And that's all I do. Okay? So now this 7 and this 8, this 7 that was the A and this 8 that was the B for the Pythagorean theorem, that's what these two differences represent. These are now officially the legs of the Pythagorean theorem. So whenever you get done subtracting your x coordinates and your y coordinates, if you have any negative differences, then take the absolute value, just chop off the negative, and then you're set to go. All right? So now, if you've got the A and the B of the Pythagorean theorem, and we didn't even need the graph over here, this is what's going to speed up the process just a little bit. But if you need that graph, absolutely use it. Okay? I'm not the type of teacher that's going to say you have to solve this problem using this particular method. Okay? If you find something that is mathematically correct, I'm okay with it. So now, again, we would have 7 squared plus 8 squared equals c squared, just like what we had down here, but we didn't actually end up solving. So now 49 plus 64 equals c squared. We can add our 49 and our 64, and that's what, 113. But we're not done yet, because we have to square root both sides to get rid of the square. And so now, again, in our calculator, this is where we're just going to do this for now, is plug this into our calculator. So the square root, nope, that's too big of a number, 113. And again, personal preference here, I'm going to do 2 decimal places. The book may often ask you just for 1 decimal place. So if this was round to the nearest tenth, we'd go 10.63, or 10.6, sorry. And if this was to the nearest hundredth, 2 decimal places, then 10.63. So I'm going to do 10.63 as our final distance between those 2 points. Okay, so here you now have 2 methods. With a graph, you can see the Pythagorean theorem in action once you draw in that right triangle, or if you have the coordinates, or maybe you need to actually get the coordinates like we did in this example, you can take your 2 coordinates, subtract your 2 coordinates, and the 2 differences that you get there are the a and the b, your legs of the Pythagorean theorem. And then you're ready to set it up and move ahead. All right, so there's 2 quick methods there. Now, there is a distance formula, and I am not a fan of the distance formula. And I'll show you why here in a second. It's very long, it's very ugly to me. I would rather use the Pythagorean theorem, in all honesty, than use the distance formula, because the distance formula is nothing other than the Pythagorean theorem. And maybe you have some experience with the distance formula. So I'm going to show you where that distance formula comes from the Pythagorean theorem. Okay? So again, we've got these 2 points. We could count this as our a and our b values, or if we subtracted our x coordinates and our y coordinates, we could end up with the a and the b of the Pythagorean theorem, right? So I'm going to start with the Pythagorean theorem. A squared plus b squared equals c squared. Now, how did we get this a value here? How did we get the a for that Pythagorean theorem? Well, that's when we subtracted our x coordinates, right? So I'm going to make a little substitution here. Where did that a come from? That happened whenever I subtracted my first x coordinate and my second x coordinate. And I'm going to put parentheses around this because I still need to square this value, if you will. And this x1 minus x2 is my a that I get here. Likewise, where does this b come from? Well, this b came from whenever we subtracted our y coordinates. So there's my plus still, right, from that plus that's right here. And so instead of b, this is where I subtracted my y coordinates. And so I still have to square with the Pythagorean theorem, right? This is like saying b squared equals, now c squared is the distance between the 2 points. And so what we're going to do now is just switch our variable from c being the hypotenuse to d being the distance. But it's still the distance squared because it's c squared, hypotenuse squared, distance squared. And we were always trying to solve for the hypotenuse, right? We were trying to solve for what c was. So how did we get rid of that square that was on the c? We square rooted both sides, right? So I can square root this side, and then I got to square root everything over here. Now, algebraically, here's where some people get tripped up. This squared cancels out with that square root. But, and this is where a lot of, again, people want to make the mistake. A lot of people will see this square root and they'll go, hey, look, there's 2 squareds under here. So that square root's going to knock out both of them. And that is an incorrect mathematical statement. And it's all because of the adding of 2 squared values. The square root can only knock out a square if there's no really adding or subtracting going on underneath that square root. Now, if there's subtracting going on within a set of parentheses, then that's okay. But this adding between these 2 squared quantities is not okay. So in the end, and now I'm going to flip-flop these 2 things, I'm going to say d, the distance, is equal to the square root of the difference of our x coordinates, quantity squared, plus the difference of our y coordinates, quantity squared. And there's the distance formula that you may or may not be familiar with. And so I'm going to have it here on the next screen, so don't worry that I'm flipping the page here. The distance between any 2 points. And again, this is nothing more than the Pythagorean theorem. But if you would rather use the distance formula, you are absolutely, positively allowed to do that. I mean, I am perfectly okay with anything that is mathematically correct. And if there are 3 ways to do a problem, hey, you pick any of those 3 ways, and I'm good with it as long as, again, it's mathematically correct. So if you want to use this distance formula, knock yourself out. What's Mr. G going to use? I'm going to use the Pythagorean theorem. Okay? But again, I leave it up to you. Now, I'm going to leave this problem for you guys to try. And if you want to use the graph, use the graph. Plot the 2 points, connect them, make your right triangle, count your vertical and horizontal pieces, and do the Pythagorean theorem. Or if you want to subtract your x coordinates and your y coordinates to get your a and b for the Pythagorean theorem, and then use the Pythagorean theorem, go with that route. Or if you're like, hey, I really like formulas, and I'm okay with memorizing formulas, but I want you to understand where the formula comes from personally. Okay, as your teacher, I want you to understand the distance formula is nothing more than the Pythagorean theorem in disguise. If you would rather use the distance formula, you go right on ahead and use that. But I will tell you, the distance formula, I've seen so many students over the years incorrectly use the distance formula, and they don't really understand why mathematically they're doing what they're doing. And so I want you to really understand what's happening. All right? All right, so you try that one out and give it a whirl.